Right. Seems like we have gone live and the first viewers are starting to roll in. Before we get started, how are you doing today, Abhishek? Excited for the webinar?
Yeah, I'm doing fine and really excited for this webinar today. So this is one of the few topics that make me really, let's say, happy to talk about.
Yeah. So
Yeah, looking
before
forward.
going too far, before spoiling it for everyone, could you tell us something that you have in store for us today? So what are we expecting to see here?
Yeah, we'll have, let's say, a simple example where first of all, we will dive into the theory just briefly, not to go deep into that, but to give the overview of the method, the harmonic balance method itself, then an example which shows the benefit and also the power of using this method over others, and then other real world examples where you see that the method is quite general and can be used for various kinds of applications. So that's the
Awesome.
plan. Yeah.
Yeah, sounds very good. And for all the attendees here, we'll dive into the webinar agenda just in 1 second, and of course the introductions. But all right, it seemed like a couple of minutes have already passed, so we could get this show properly started. So indeed, welcome everyone on my behalf to our webinar on accelerating nonlinear MEMS simulations with the harmonic balance method. I'm Jukka Knutinen, the head of marketing at Quanscient, and I'll be as the host, the MC here, if you will. And with me, I have Dr. Abhishek Deshmukh as the technical speaker. Now, before, but actually, without further ado, let's get into what we're doing here today and what's going to happen. So before we get started, there's just a couple of housekeeping items that you might be actually very interested in. So first of all, we want to keep this as a very not only a one-way street where we show you stuff, but also at any point when you have questions or even comments, we'd very much want to encourage you to type them into the chat or into the questions tab. So for the questions tab, you can direct your questions to either myself or Abhishek, or in the chat you can give your general comments if you have those. And please do submit your questions at any time during the event. So we will be addressing them throughout the event. So basically have this what you could call a continuous Q&A. But in addition to that, we will have a dedicated Q&A session at the end. Now, other thing is that we will be handing out some resources for you guys during this live event. So we'll just take in a second from now. We'll check what those resources are. But you can see this material tab on your hopefully right hand corner. So in the right, so you will have this material tab. So there will be some resources, some PDF documents that we will be giving out to you later in the show. So again, I'm Jukka Kuntinen, work as the head of marketing at Quanscient, and with me for the technical portion of today, we have Dr. Abhishek Deshmukh. Now, would you mind introducing yourself, just a couple of sentences on who you are, what you do?
Yeah, thanks, Yuka. My name is Abhishek Deshmukh. For those who have not attended previous webinars, so I'm team lead of application engineering at Quanscient, mostly dealing with multiphysics applications, including harmonic balance method applied to different, uh, let's say, multiphysics applications like acoustic structure interaction and yeah, basically that. And I have, let's say, my background is in fluid dynamics, turbulent flows, and uh, yeah, in those topics.
Awesome. Now, we already covered the agenda just slightly, but let's do it a bit more officially here. So, indeed, just 5 minutes of welcoming and a couple of housekeeping items before I give it to Abhishek to actually go into the topic of today, which is the harmonic balance method. And before going into the actual live demos or applications of it, just 5 minutes of theory. So just so everyone has the background and introduction to what the actual method is and how it differs, for example, from transient analysis. So a couple of working principles there. And then indeed it is the live demo. So what will actually be covered. So how the harmonic balance method is actually applied in practice. So we'll see a demonstration of that. And then, as Abhishek said, other applications and real world results to show the versatility of the method to other MEMS applications as well. Then we'll have the dedicated Q&A session and the conclusion and key takeaways. Just a couple of words on the handout. So these are the documents we'll be giving out. So there will be this our actually previous harmonic balance method webinar PDF summary looking like this, and then our webinar summary, PDF summary of our previous webinar. So actually this MUTS webinar with our UK director, Dr. Andrew Tweedy. So some very, very nice examples here. And you'll definitely want to get this. So I will be pasting them into the materials tab later on as we go. Now, just a very, very quick introduction to the actual tool that will be used today to actually apply the harmonic balance method. So for those of you who don't know, that tool is Quanscient Allsolve. So that is a cloud-based FEM multiphysics software developed by Quanscient, which is a company established in 2021 here in Tampere, Finland, and built upon the open source solver Sparse Lizard developed by a CTO, Dr. Alexander Halbach. Now, why Quanscient? Why are, for example, companies like this using Quanscient? Well, the key benefits are in the cloud-based nature of the tool, which basically allows for driving confident design decisions through taking into account real-world conditions and manufacturing constraints. So you can run simulations, these Monte Carlo simulations, parallel simulations of up to 1,000 or even more. Results can look like this. You can accelerate the engineering productivity through basically exploring more design options and optimize the product performance. Can, for example, look like these. And by the way, I will be sending out these slides to all of the attendees here, so you can have a closer look at these examples here. And finally, yeah, you can scale your simulation resources up or down with no license restrictions, and use the API to build and automate design workflows, for example, as like this. So that's a crash course into Quanscient also for those of you who don't know and why it's used nowadays. But with that, I'd like to give it to Dr. Deshmukh here to actually get into the topic, so the harmonic balance method. So go ahead, Abhishek.
Thanks a lot, Yuka. That was a very nice introduction to the tool, and let me share my screen. All right, so thank you everyone for joining this webinar from my side, and let's have a look at what today's webinar is about. It's the harmonic balance method. So some of you might already know what this method is about, but I would like to give some introduction and background for those who have not heard before, or like me. uh, I started learning about this method not long ago, like 1 year before today. So and when I really realized the potential of the method, I instantly became a fan of it, and always tried to find applications where I could use this method as much as possible. So what's this is about? So it's a numerical method to solve the nonlinear periodic problems, and mainly this is in the frequency domain. So uh, we regularly solve these linear problems in frequency domain, but for nonlinear effects, it's not easy to just represent uh, these effects with one frequency resolution. and that's where the harmonic balance method comes in the picture. The method itself has been there since 1970s, so it's not a new method. It has been there, has been used for lumped models. The main roadblock on applying this model for finite element method has been the hardware limitations. So mainly the bottleneck, the bottleneck was the memory bandwidth and the power of let's say the let's say the resources. So the demanding resources that were not available until recently. And with the advent of cloud computing or even the high performance computing, uh, we are now able to access on demand cloud resources, and with our efficient implementation in Quanscient Allsolve, we are able to use the or apply the harmonic balance method in for a finite element simulation, and trying to use this and make good use of the method for the benefit uh, of our users. So let's take an example to dive a bit deeper into the method. So here I have on the right hand side a spring mass damper system. It's quite simple system that we usually start with when we try to understand some let's say some example. And it's an electrostatically actuated system. So you see two plates, parallel plates, joined by a spring and damper, and then the voltage applied across these two plates. And what happens is that there are some non-linearities appearing in the system itself due to two main things. First, the mechanical motion itself, and the second one, the electrostatic force that is created due to the potential difference here. And as a rule of thumb, this force is kind of proportional to square of voltage, and that's where the one of the non-linearities that come into picture. And we'll see how that can be taken into account using this method. Before that, so why harmonic balance and why not use transient? So yeah, there is possibility to use transient analysis if there are non-linearities in the system. But as you can see on the picture here, I plotted a deflection of, let's say, a simple disk over time for a, let's say, um, for the example that was shown before. And as you can see, there is an initial transient that needs some time to stabilize until we reach to the steady state periodic let's say response. uh, and this time, as we'll also see in one of the examples that I'll show, this can be quite significant. So it can be easily more than 1,000 cycles in practical cases to reach the steady state, and where you can actually make Fourier analysis or transform this data into frequency domain, and then try to look at the frequency response there. And this will also involve manual steps to extract this data, try to see where or at what time you reach the steady state. And another problem is when you have this data, there is always noise involved due to numerical precision and whatnot. And extracted frequencies from this would have this noise. And we will see that harmonic balance method provides quite nice solution without noise and such. So the key working principle of the harmonic balance method is that we simply decompose the fields into their Fourier coefficients. So as you can see on this slide, we can decompose a field phi, which is a spatial and temporal field, in terms of these Fourier coefficients. So the sinusoidal part and the cosinusoidal part, with with frequency associated with that. And we can use uh, as many, let's say we call these harmonic coefficients, and as many coefficients as needed to represent, or to let's say accurately represent the field. And many times we already know how many harmonics we expect in the system, and that way we can try to reduce the number of coefficients that we need. And as said here, for higher harmonics, so for simply stating, the harmonic method is using just first two terms at fundamental frequency. And to consider non-linearities in the system, we have to consider also the higher harmonics at higher frequencies, which contribute to the field itself in the nonlinear regime. So what does it mean to have the linear or non-linear regime? So here I plot, for example, for the same spring mass damper system driven by 10 volt DC current, and 10 volt DC voltage and 1 volt AC component on top of that. And you can see that the deflection or the response in transient is quite periodic, that we don't visually see any nonlinearities in the signal. And when we transform this to the harmonic domain, we can see that the coefficients which represent this Fourier series, we see the first constant part C0, and then the first harmonic coefficient for sine and cosine, and the rest after that are almost zero. And that's why we don't see any deviation compared to the sinusoidal signal there. And as soon as we add, let's say, we increase the amplitude of AC drive on top of the constant DC part, we see a different signal where we have now plateaus and valleys. And the plateaus are kind of broad here. And for this, if we see in the harmonic coefficients, or the harmonic domain, we see that there are contribution from the constant part, then the first sinusoidal, and then we see that there is cosine of cosine at twice the fundamental frequency appearing in the harmonic domain. And that means we have to consider this term in the decomposition, field decomposition, and rest can be neglected. All right, so that's the basic principle, trying to decompose the field and try to see how many harmonic coefficients are needed to reasonably represent the field that we are interested in. Now let's go into the live example. Here I chose CMUT, so-called capacitive micro machine ultrasound transducer. And this ties up really nicely with the previous webinar we had on the MUTs. So if you are interested in details of these devices and their application, or the Allsolve application to these devices, please feel free to have a look at our previous webinar. And these are kind of let's say MEMS devices, which, for example, on this slide you see an array of CMUTs, which could be potentially used for ultrasound imaging, or medical devices, or measurement, or even some wearables. And these can be used to create the let's say ultrasound or acoustic waves in the medium they are exposed to, and they can be also used for the reception. So these are kind of send receive, let's say, devices, and these are electrostatically actuated. So this also ties up well with the example, the simple example we saw before, and let's have a look at now the actual demo. So here I chose a single cell. I'm not going to simulate the whole array of CMUTs. The point of this webinar is to focus on the method, so I chose a simple example of CMUT from one of these, let's say. and let's have a look at that now. um, I hope you
We,
see my.
yes, we do see the screen. And just wanted to remind everyone that if and when you have the questions, you can indeed simply type them in the questions bar and we'll address them uh, live when you still have them burning in your head. So please don't hesitate to actually ask the questions when they appear. But that's it. And but just a quick reminder that we will be indeed handing out the MATS webinar PDF, including the CMUT example, which Abhishek just referred to. So stay tuned for that. But all right, back to you, Abhishek.
Thanks for that reminder. Uh, yeah, so let's have a look at the example, CMUT example. It's basically quite simple. Uh, to save some time and focus on important parts, I created this project on our platform. Already populated some of the things that might actually uh, uh, so the some of the things that we regularly set up, and they kind of not relevant for the webinar topic itself. So mainly creating the disk geometry. So we have two parallel plates or two parallel disks here, and you can see that they are kind of quite large in the other, or the in in one dimension, let's say, or two dimensions, and very thin in the third dimension. And this is also typically the case in such devices. And between these two plates we have a vacuum cavity. uh, Although I don't have, I'm not modeling the surrounding part here to enclose the vacuum, or to seal the cavity with that vacuum. But yeah, have a look at how this was created. So first I created the variables, so-called variables that we have here. For example, the plate thickness, or the top plate thickness, then the radius of the CMUT. In this case I chose 167 micrometers, and this is, by the way, from literature. So that's why these odd numbers, trying to match what they produced in their papers. So basically defining the gap frequency, the AC voltage. So here you can see the AC drive is about 0.1 volts. Then the DC part, that's the bias voltage. Then the spring constant. In this case, I've chosen to represent the CMUT, or the top plate, as a rigid one, and then the spring attached to that. Some volume calculations that we'll need, for example, to compute the fundamental, or the resonant frequency. This we'll use for normalization and such. Some damping coefficient and pull-in voltage. That's the highest voltage that you need to cause the two plates to collapse in these CMUTs. And yeah, that's all we need. Using those parameters, I created a parameterized geometry, and then set the materials. Here I use silicon, monocrystalline silicon for the top plate, the silicon nitride for the bottom, uh, and vacuum between the two plates. Uh, Then moving on to physics tab. Here we'll spend a bit more time to understand what all we need to simulate a CMUT cell in this case. So we need a solid mechanics. So this is applied to solid parts. Then we need electrostatics, which is applied into the gap here. That's where the electrostatic force develops. And then we need also mesh deformation, because as the plate is acted upon by the electrostatic force, it is moving towards the bottom, and then we need to consider the effect of this changing gap on the electrostatic force itself, and that's one of the, or that's basically the non-linearity that is coming into picture in this case, in addition to yeah, the mesh deformation itself. uh, so let's have a look at the interactions or boundary conditions that we need to set. So the clamp, we clamp the bottom plate, then we constrain the top plate. So I don't want this plate to move in the sideways direction, I want to move it just in the z direction, so I constrain it in other two. Then apply a spring to the top of this plate using circuit coupling. This is this circuit, or the spring is attached to this in via lumped ports, so-called lumped ports, where you can specify simple relations like force. Here, as you can see, force equals k minus k times the displacement. And this is not all. You can also use the ordinary differential equation simply using, for example, these functions, and then it's quite easy to apply these external circuits as the ODEs to these lump ports. Then electric force, which is the coupling between these electrostatics and solid mechanics. Then some damping. So real life systems always have some damping, and this is also kind of helpful in terms of for the solver itself, in the regions of resonant frequencies. Then the large displacement, which considers the effect or the nonlinear effect of the electrostatic force. On the electrostatics, we apply the sinusoidal AC part on top of the bias voltage, that's the DC part, and this is applied to the top of this cavity. Uh, then at the bottom we have the ground, and again the large displacement interaction. This is basically coupling to the mesh deformation, which is applied to the gap itself, because the gap will be deformed, and we need to consider, we need to smoothen out the effects, the mesh there. And this is constrained by the solid on the top and bottom, and on the sides again, we don't want the mesh bulge out of this, and we constrain it to that circumference. All right, so that's about the physics and boundary conditions. Now let's go to the
Sorry,
setup.
Abhijit, just
Yeah,
to quickly comment, there was a question
yeah.
uh, on the actual uh, future plans for the harmonic balance. So basically, the question was: is there a plan to extend the harmonic balance method with other expansion series than just the Fourier series? So, for example, a wavelet balance method for certain applications where randomness is important to the step functions. So, is there any plans there?
I'm sure there are plans, or those methods might be on the roadmap. At the moment, we are not. I mean, it's not in the immediate future, but of course, in the, let's say, long term, there might be plans to also bring such, let's say, complex methods to the platform as well.
All right, thank you.
Um, yeah, so stay tuned to our updates, and you will know. Thanks for the question, by the way, and let's have a look at now the setup of the harmonic, let's say, balance itself. Before that, we have to create the mesh. Let's create that quickly. I'll just go with the basic settings, and as I mentioned, these are thin geometries, or thin in terms of the dimensions in the z direction, and typical MEMS devices always have such thin dimensions. And these, for such kind of geometries, we have this layered or extruded meshing, and as you can see, I'll just try this extruded meshing here, and we'll see how the mesh looks like now. And let's have a preview. So in the XY plane you see the triangular mesh, and this is now extruded through all the 3 layers up in the Z direction. And if we look closely, we can see that there is one layer on the top plate, the one on the bottom, and the gap in the middle is meshed with 5 layers. The other 2 you don't see because there is the color of the edge is different or very similar to other domain itself. Then we add the simulation. Let's name this as a frequency sweep. Then we choose multi-harmonic, so that's same as harmonic balance, which is, this is not the popular name, as we call it for the consistency of the naming. We chose to name this multi-harmonic. And we have this frequency, so the fundamental driving frequency. Here's where we have to choose the harmonics that we want to represent in for this case. So I'll choose the constant harmonic. Then 2 is the sinusoidal coefficient, 3 is the cosinusoidal coefficient for the fundamental frequency. Then we also need 1 or the twice the fundamental frequency, sine and cosine. And this is because we know that this is what we expect in the system, and but there is no limitation that you cannot choose higher harmonics. I can also cherry pick, for example, 100th harmonic, and that will be represented without going through all the harmonics in between these two, 5 and 100. So that's also possible. Let's have some 50 examples or samples there. I'll choose fast start, and that's all. Basically that's all you need for the setup of harmonic balance. Choose the harmonics, set fundamental frequency, set the samples. Typically the samples are twice or thrice the number of harmonics that you choose here, the highest harmonic that you choose. And yeah, for evaluation, let's add some outputs. So the harmonic, then some integrated output, so that we can have a look at the let's say what's the displacement. So I'll just quickly add, let me check to save some time, I'll just copy and bring the outputs from my pre-run project. Yeah, so I just chose the harmonic 2 and harmonic 3 and trying to get the magnitude of that, and then max value over the spatial domain. And then to normalize the frequency, so the normalized frequency is divided by f0, and I think that's all we need. And for sweeping, we have to add the functions here. So we have to add the sweeps over frequency, and here we can basically add the frequency sweep. So let's add some lane space. So going from 6.6 megahertz to 1 megahertz in the steps of 40 values, and then override, that's the DC voltage I want to choose for this case. Let's choose the 1 volt as DC voltage, and let's have a look what comes out from here. So as we are, I think I forgot to add the sweep here. So we have to apply sweep and override. I think just sweep in this case. And yeah, so as we are speaking, the jobs are submitted to the cloud, and they are already starting to run. Most probably I have possibly forgotten to add something, but I have some free pre-setup which I just finished before this webinar, and here I have the logs, so we can take a look at the logs to check the history of convergence, and we can see that one of the simulations finished in 13 seconds. Typically, the simulations which are close to resonance, they take longer. Like we can also see the plot here. So the max displacement over the frequency, which is normalized. So at 1, this should be the resonance frequency. It's slightly lower than the resonance frequency because we added the proportional damping, which shifts the peak towards left. But in general, we can add um, any kind of damping, including the squeeze film damping, which is not covered here, but we'll see that it was done in the previous harmonic balance webinar for the Microspeaker case. And yeah, that was the frequency sweep, just to see if we are in the right ballpark. And then the double sweep, as I call it, that's for the sweep over frequency and as well as the um, frequency and the DC voltage. So in this case, I know the pull-in voltage is about 16 to 7 or 17 volts. So before so up to 15, I chose these steps, and this is now I in Allsolve we have this rep element and rep mat, which can create those 2 by so the matrix of simulations basically. So we have 40 frequencies, and for each of these frequencies 7 steps in voltage. So that's our double sweep. And when we look at the plots here, uh, I added um, a logarithmic scale here to to exaggerate the lowest voltage case here. But as you can see here, we have the fundament or the resonant frequency close to 1, and as we start increasing the bias voltage, the resonance frequency is shifting towards left, and this is what we call this is basically the behavior that's quite expected in these kind of CMUTs, and that's due to the non-linearities present in the system. All right, so that was the um, live demo. Let's go back to now what we have here as the comparison with respect to transient. So as you saw, these simulations take quite literally seconds or max. If I remember, the max time that one simulation takes for these cases is about 200 to 300 seconds. And if you see the transient here, you can see that we need up to 1,000 cycles to capture this trend accurately, and one of these transient simulations each takes about 3 hours. So there is clear benefit of the harmonic balance using harmonic balance method for such cases where we see the spring softening effect, basically reducing the spring constant of the system as we increase the bias voltage. And yeah, that was the end of the live demo section. And let's
So yes,
yeah.
so before going actually into the next section, I could give out the PDF summary for the MUTs webinar right about now. So just let me find it here.
And if you have questions up to this point, feel free to put them in the chat.
Yes, so there we go. So yes, I'm uploading it now to the materials tab, and you'll be able to just download it there, uh, and check it out after the event. So that is there now, and just in a moment I'll give you the other one too. So the previous harmonic balance uh, webinar PDF summary. But that's it from my part. Back to you, Abhishek, once again.
Thanks again. So let's say we applied this method to CMUT now. So is that, as I said before as well, so this is quite general method. It's not the application specific. It's a as any other numerical method. This is applicable to various applications, and we'll see a few applications that I tried to use this method. And first application is the AC Joule heating, so which we commonly see in our household uh, equipments, for example your heaters, electric heaters, or some equipments, or even smartphones, that wherever you have the alternating current flowing through a conductor which has some kind of resistance, you will get some form of heating there. And yeah, in this case I chose here a small filament, as you see, square filament, and tried to run some transient simulations at fundamental driving frequency of 100 and 400 hertz. And you can see the plots here. The plots show the maximum temperature over time as we apply the sinusoidal uh, AC uh, current through this filament. And you can see that initially it needs some time to stabilize to certain level. The temperature values are not the absolute ones, these are relative with respect to the reference temperature. And you can see that for the for the frequencies, you see a constant max temperature that is reached after certain time, and about that we have fluctuations. And this constant is kind of provides the heating effect that we see in the day-to-day examples or applications. And the same simulations now I do with the harmonic balance method. Here I can do much more with the same method. I did here 40 steps from frequency 1 hertz to 500 hertz. And what's plotted here is not the actual temperature but the harmonic coefficients. So as we saw, there can be up to 5 harmonic coefficients, that in this case also used five harmonic coefficients, and that's what are shown here. So we see the blue, that's the max T1, that's the constant part, which is what represents the constant heating that you get from here. Then the max T2 is the second harmonic, that's the harmonic coefficient for the sinusoidal signal at fundamental frequency. And you can see that that coefficient is essentially zero, which means we don't have any contribution from the sinusoidal part at fundamental frequency. And same thing for the cosinusoidal here. But what is nice to see here is that we see that, which is not evident from the transient simulations because we cannot see the frequency directly from this plot, but you can clearly see that the T4 and T5 are the sine and cosine parts at twice the fundamental frequency, and they have contributions which can vary over frequency, and one part becomes dominant over the other depending on how what your frequency is. And this is clearly demonstrated by the method itself here. To look at why we get this, we have to go a bit deeper. I'll just try to touch a bit there. So our heat source here is proportional to the current square, and if we try to put in the sinusoidal signal of current here and do the trigonometric math, we end up with what we have here as the temperature which has some constant heating plus the sinusoidal part at twice the fundamental frequency. This is what you see 2 times f0, and the same cosine at twice the fundamental frequency. And these are basically T4 and T5 coefficients that you see. And the first part, that's the blue constant part there. And yeah, then other application is in the structural or the vibrational analysis. Here I have the clamped beam. It's a simple beam clamped at both ends, and in this case the material or the mechanical resonance can have the can can due to the non geometric nonlinearity or the stiffening that you might get due to the displacement, the large displacement itself. You can have uh, you can have basically different solutions for the same frequency, and both of these or multiple of these solutions can be valid. And if we try to model this in a linear way, you get what you see on the left bottom here. That's the displacement or the max displacement of the beam over frequency. You get standard resonance peak, and that's all, without considering the geometric nonlinearity. And as soon as you add the nonlinearity to the system, as I said, for the same frequency you can get, for example, for 170 hertz here, you can get 3 solutions, and all of them are valid solutions. That's just the behavior that is represented by this system. And it's not easy to capture this curve basically in transient, but with the harmonic balance method you can easily do this in one simulation. If you are interested in details of this example, uh, we covered this example in our previous harmonic balance webinar in detail. So please have a look at that. um, yeah, so that's quite interesting application that I see. And uh, there are then other applications, for example, Microspeaker. uh, these days we have like there is emergent trend of using silicon based microspeakers, or because of some obvious advantages that they provide: crisp sound and better control over the response. And these are typically electrostatically actuated, and also in some way you can represent. For example, here I show an schematic from the literature that I took this example from. And these speakers have simple parallel plates that are as shown on the right hand side. One of the plate is moving and one is fixed, and these plates, that's the motion of these plates creates the let's say motion of waves or air waves, and which is perceived by us as a sound. And these are inherently nonlinear because we have to simulate the fluid dynamic or airflow within these small gaps. And we applied this harmonic balance method to this example, which involves now three types of different physics, including the fluid dynamics. And this we were able to capture the displacement, which is like measurable, and compared with the literature, and you can see that there is reasonable match there. And as I said, because of the computational advantages, you can perform the parametric sweeps as shown as an example here, for example over frequency and voltage, trying to map the optimal operating points, and the trying to gauge your design space that you are interested in, for example. And yeah, um, and the last example I have is, so far we looked at the MEMS, so-called MEMS examples, and wanted to also have some kind of non-MEMS or bigger example here, it's a loudspeaker, where we have electromagnetics in the and the acoustic structure interaction, which is kind of very complex multiphysics problem, and we can do this in Quanscient Allsolve, fully coupled and in frequency domain, considering all the nonlinearities of the system. As an example, what I show here is, if you have an input signal, which is shown here in the center, uh, the dashed line is simple sinusoidal signal, and the corresponding output of the pressure from the loudspeaker is also shown in the dashed. You get the standard response, which is linear. As soon as I add a small component of, actually equal component but slightly different frequency, you can see that the input signal is changed, so-called intermodulation. And although the frequencies are not so different from each other, you see that in the output signal there are lot more other or higher frequencies appearing as a result of this intermodulation. And this is easily captured by the harmonic balance method, by incorporating those higher harmonics in the simulation. I think with this, we are done with the real life examples. Yuka, over to you.
Thank you, Abhishek. Now, yeah, awesome presentation, awesome examples. Now, as promised, we could go ahead and paste the previous harmonic balance webinar in the materials tab, which is there now. And actually, before going into the Q&A, you can, of course, already think of the questions in your head. We have a question for you. So basically, the question is, do you utilize the harmonic balance method in your current simulation work? So that is the question that is on the screen right now, and which we would be very interested in seeing. So how many of you in the audience actually utilize the harmonic balance method, whether you do, or if you don't, do you recognize the value in the harmonic balance method, or that you are just fine without it? So would be very interested in seeing. So yeah, the poll is right there on the screen. So go ahead and let us know. Give you just a couple of seconds here to answer. We're getting a bit of each. So a couple of yeses, a couple of nos, and so on. Let's see if we can get a few more votes in before closing the poll. All right, just last seconds. All right, now results are in, and basically it's a bit of each, as said. All right, so some do, some recognize the value, some are actually fine without it. That's perfectly fine. Now, one last poll that we want to ask you guys, so specifically for those who see the value but don't use it, is whether you'd like a personal demo of the harmonic balance method to your specific application. So whether you'd like to know how it works for your case specifically, and what kind of like actual business benefits you could see from the method applied to your use case. So if that is something that you would be interested in discussing or exploring further, then let us know. And no worries, these results won't be shown on the screen. So just leave that there for a second. Now, in the meantime, we still have a bit less than 5 minutes. So before wrapping everything up, we'd like to still address any of the burning questions that you might have. So anything regarding the harmonic balance method, its applications, uh, or anything else regarding that matter. So, at least one question that comes to me, as let's say a layperson in this case, is that is the harmonic balance method always better than the transient analysis, or are there indeed cases where you would opt for the transient analysis?
Yeah, that's a very good question, Yuka, and also natural one. I also had the same question, and I tried to find the answers to that. One typical case where the harmonic balance method would not be useful is kind of the impulse response, because there is kind of a step response that you have to provide, and to capture the, let's say, step response, you will need practically quite large number of harmonics to and that's where the limitations of this method come in. So in those cases, it would be practical to use transient simulation, just sheerly out of the computational demands. um, but where you have, let's say, where you see a periodic signal which need not be perfectly, and as I have shown also in my presentation, uh, is if it's periodic, and you have few harmonics, if you can represent that signal with few harmonics, that's the perfect, let's say, case to use this method. So you will reach, or you will get most benefits out for those cases.
Awesome. Well, then there was a question about the computational times of the fluid flow simulations you showed. So anything you can share
Yes.
about those?
Yes, so for these cases, this has actually improved quite a lot with the recent development by our team. This was previously 30 minutes, and we have speed up. This is actually a conservative estimate that I put in. We have gone up to 14 times speed up from, let's say, what we had a few months ago. So we are constantly upgrading, or if we are constantly optimizing our implementation without compromising the accuracy. And as you can see, the massive, I just took 4 times here just to be on safe side, but we can achieve up to 14 times speed up without um, yeah uh, compared to the previous implementation that we have.
Awesome. Very impressive. Now, as it is that we have just a couple of minutes left, just like to summarize quickly on the practical side of things. So basically, a few minutes after we end here, I will be sending you the all of the speaker slides that we covered here. Uh, what else? You'll be receiving the recording of the event and a PDF summary of this event uh, either later in this week, maybe not the PDF summary, but at the very least early or mid next week. So stay tuned for that. And yeah, at this point, like to thank everyone who tuned in, all of the questions, engagements, and others, and of course, thank you, Abhishek, for an awesome presentation. In just overall, very nice.
Thanks, Yuka.
Now, if there's nothing else, then I'd like to wish everyone a happy rest of the day, and hope to see you in the next webinar. So thank you and bye bye.